Wherever you are right now, whether you're settling into bed, resting on a couch, or simply letting the day loosen its grip, you're very welcome here. Tonight, we're going to take a calm, unhurried look at something that sounds simple at first, but quickly becomes surprisingly difficult to picture once physics gets involved. We're going to explore how big Alpha Centauri really is. Not big in the dramatic science fiction sense, and not big in the way headlines like to exaggerate, but big in the precise, quietly stubborn way physics defines size, distance, mass, and space itself. Because when astronomers talk about size, they're rarely talking about just one thing. They're talking about how much mass is involved, how far objects are separated, how gravity binds systems together, and how energy moves through empty space. And Alpha Centauri, despite being our nearest stellar neighbour, manages to stretch every one of those ideas in ways that resist intuition. Before we go any further, it's worth taking a moment to notice where you are. Maybe the room is dim, maybe the lights are already off, maybe there's a faint sound in the background, a fan, distant traffic, or the quiet hum of electronics. Where are you listening from tonight? And more gently, what part of the day or night are you moving through right now? It's interesting to think that while you're here, grounded in a single place, the topic we're exploring exists far beyond anything your senses can reach directly, separated from you by distances that don't behave the way everyday distances do. If you find this kind of slow, careful exploration calming, or if it helps you unwind as the day fades, you might consider liking the video or subscribing. It helps this small, quiet corner of science reach others who are also looking for a peaceful way to think about the universe. There's no rush though. Nothing here requires urgency. Physics, after all, is very patient. Now, Alpha Centauri is often introduced as the closest star to our Sun, which is true in a general sense, but that phrasing already hides a lot of complexity. First, Alpha Centauri is not a single star. It's a star system, bound together by gravity, made up of multiple stars moving through space in an intricate orbital arrangement. And second, closest in astronomy still means unimaginably far away by human standards. So before we even attempt to answer how big Alpha Centauri is, we need to slow down and clarify what we mean by size in a physical sense. In physics, size can refer to several related but distinct quantities. There is physical size, meaning the actual radius and volume of an object, how much space its matter occupies. There is mass, which tells us how much matter is present and how strongly it interacts gravitationally with other objects. There is distance, which describes separation through space, not just between us and Alpha Centauri, but between the stars within the system itself. And there is scale, a more subtle idea that describes how these quantities compare to familiar reference points like our Sun, our solar system, or even the orbit of Earth. Alpha Centauri challenges us because it combines all of these at once. It's a nearby system that still lies far outside the reach of direct travel. It's made of stars similar to our Sun, but arranged in a way our solar system is not. And it exists within a region of space that feels empty, yet is governed by precise gravitational relationships that physics describes with quiet confidence. At the heart of the Alpha Centauri system are two stars known as Alpha Centauri A and Alpha Centauri B. These two stars form what physicists call a binary system. They orbit a common center of mass, a point in space determined by their relative masses, rather than one star orbiting the other in a simple way. This already tells us something important about scale. The distance between these two stars is not small. Over the course of their orbit, their separation varies significantly, sometimes bringing them closer together than the distance between the Sun and Pluto, and at other times pushing them much farther apart. From a physics perspective, that separation matters more than their visual appearance. When we look at Alpha Centauri through a telescope, especially from Earth, the stars appear close together, sometimes even overlapping as points of light. But that closeness is an illusion created by distance. In reality, the space between them is vast, filled with extremely low-density interstellar material, mostly hydrogen atoms spaced far apart. The gravitational connection between the stars spans millions of kilometers, yet the region between them is emptier than any vacuum we could produce on Earth. Orbiting much farther away is Proxima Centauri, a smaller, cooler star that is gravitationally associated with the main pair, though its orbit is so wide and slow that its relationship to the system is still studied and debated. From a physical standpoint, including Proxima dramatically increases the size of the Alpha Centauri system, not because Proxima itself is large, but because of how far it travels from the central pair during its orbit. The system's gravitational footprint extends across an enormous region of space, far larger than the physical size of the stars themselves. Already we can see that asking how big Alpha Centauri is depends on what boundary we're interested in. Are we talking about the radius of the stars measured in kilometers? Are we talking about the distances between them measured in astronomical units? Or are we talking about the full gravitational reach of the system, which extends even farther into interstellar space? Physics allows all of these definitions, but it doesn't collapse them into a single simple number. Then there's the distance from us. Alpha Centauri is about 437 light-years away from Earth. That number is often quoted but rarely unpacked. A light-year is not a unit of time, it's a unit of distance defined by how far light travels in 1 year through a vacuum. Light moves at approximately 290 kilometers per second. Over the course of a year, that adds up to roughly 9.46 trillion kilometers. Multiply that by 4.37, and you get a distance so large that writing it out in full stops being helpful. In physics, distances of this scale are not meant to be imagined directly. They're meant to be handled mathematically. The equations work cleanly even when the numbers are enormous. Our intuition, however, struggles. If Alpha Centauri were scaled down so that the Earth-Sun distance fit inside a small room, Alpha Centauri would still be hundreds of kilometers away, and yet, in cosmic terms, it's practically next door. There are regions of the galaxy where stars are separated by far greater distances. This contrast between human scale and physical scale is one of the reasons Alpha Centauri is such a useful system to think about. It sits right at the edge of what we can reasonably talk about without losing all connection to everyday experience. It's distant enough to stretch the mind, but close enough to be measured with precision. Astronomers have determined its distance using parallax, a geometric method based on observing slight shifts in a star's position as Earth orbits the Sun. This is pure physics and geometry, no speculation involved, just careful measurement and repetition. And yet, despite all this measurement, the word big remains slippery. The stars themselves are not unusually large. Alpha Centauri A is slightly more massive and slightly larger than the Sun. Alpha Centauri B is slightly smaller and less massive. Proxima Centauri is much smaller, a red dwarf with a fraction of the Sun's mass and luminosity. If you were to line them up by physical size alone, none of them would stand out as extreme. They are ordinary stars by stellar standards. What makes Alpha Centauri feel big is not the stars themselves, but the space they command. The orbital distances, the gravitational relationships, the volume of space within which their mutual influence dominates. In physics, systems are often defined not by the objects alone, but by the forces connecting them. Gravity does not stop abruptly at a visible edge. It fades gradually, extending outward indefinitely, growing weaker with distance but never fully vanishing. So when we ask how big Alpha Centauri really is, we're also asking how far its gravity matters, how wide its orbits stretch, and how much space must be considered part of the system for physical descriptions to make sense. These are not philosophical questions. They're practical ones in astrophysics, especially when studying how stars form, how systems remain stable over billions of years, and how planets, if present, might move within such environments. For now, it's enough to hold one idea gently in mind. Alpha Centauri is not big in a single way. It is big in layers, big in distance from us, big in the space between its stars, big in the region of gravity it occupies, and at the same time made of stars that are familiar in size and behavior, following the same physical laws that govern our own Sun. As that thought settles, we can begin to shift our attention more carefully toward what physics really means when it talks about size, and why everyday language so often fails us when the universe refuses to stay small. When we ask what it means for something to be big in physics, we're stepping into a question that sounds simple, but quickly resists any single answer. In everyday life, size feels straightforward. A car is bigger than a bicycle. A house is bigger than a room. We compare objects by how much space they visibly occupy, and our intuition works well because everything we deal with exists within a narrow range of scales. Physics, however, does not have that luxury. It deals with things that range from subatomic particles smaller than anything we can see, to structures so vast that even light takes years to cross them. In that context, big becomes a layered concept, one that depends entirely on what property you're measuring and what you're comparing it to. One of the most important distinctions physics makes is between size and distance. These words are often blended together in casual conversation, but they describe very different things. Size refers to the physical extent of an object itself. It's about radius, diameter, surface area, and volume. Distance, on the other hand, refers to separation. It tells us how far apart two objects are in space, regardless of how large or small those objects may be. A small object can be very far away. A very large object can be relatively close. In astronomy, confusing these two ideas is one of the quickest ways to lose your sense of scale. Take the Moon as an example. The Moon is about 3,474 kilometers in diameter. That makes it large by human standards, but small compared to planets like Earth. Yet the Moon appears roughly the same size in the sky as the Sun. This isn't because the Moon is large, but because it's close. The Sun is vastly bigger than the Moon, with a diameter about 400 times larger, but it's also about 400 times farther away. The apparent size we perceive is a balance between physical size and distance. Physics separates these cleanly, even when our senses blur them together. When we talk about Alpha Centauri, this distinction becomes unavoidable. The stars in the Alpha Centauri system are physically similar in size to our Sun. None of them are supergiants or exotic extremes. Yet Alpha Centauri feels enormous to us because of its distance, and because of the space involved in the system itself. The bigness comes not from the stars swelling to impossible proportions, but from the scale at which they are separated from one another and from us. Another layer of meaning comes from mass. In physics, mass is often more important than size. Mass tells us how much matter an object contains, and how strongly it interacts gravitationally with other objects. Two objects can have similar sizes but very different masses. A balloon and a bowling ball might be comparable in volume, but their masses and gravitational effects are wildly different. In space, mass determines orbits, stability, and long-term evolution. When physicists assess how big a system is in a functional sense, they often mean how much mass it has and how that mass shapes the surrounding space. This is especially important when dealing with star systems. A star's mass determines how hot its core becomes, how fast it burns fuel, how long it lives, and what kind of remnant it leaves behind. In the case of Alpha Centauri, the total mass of the system matters more than the individual radii of its stars when it comes to understanding orbital dynamics. The gravitational dance between Alpha Centauri A and B is governed by their combined mass and how that mass is distributed, not simply by how large they look in a diagram. Scale adds yet another dimension. Scale is not a single measurement. It's a relationship. It tells us how one size compares to another, how one distance fits within a larger framework. In physics, scale is often what determines which laws dominate a situation. At very small scales, quantum mechanics becomes important. At human scales, classical mechanics works well. At astronomical scales, gravity and relativity start to shape behavior in noticeable ways. Something can be big on one scale and small on another without contradiction. For example, Earth is enormous compared to a human, but insignificant compared to the Sun. The Sun, in turn, is massive compared to Earth, but modest compared to many stars in the galaxy. And the Milky Way galaxy itself, containing hundreds of billions of stars, is just one among trillions of galaxies in the observable universe. Each step outward changes what big means, not because the word is vague, but because context shifts. Physics handles this by choosing reference points carefully. Astronomers rarely describe distances in kilometers when dealing with stars, not because kilometers are wrong, but because they become unwieldy. Instead, they use astronomical units, light years, or parsecs. An astronomical unit is the average distance between Earth and the Sun. It's useful for describing planetary systems. A light year is useful for describing distances between stars. A parsec, defined through geometry and parallax, becomes useful for mapping larger regions of space. Each unit reflects a change in scale, not a change in reality. This scaling also applies to size. Stars are often described in terms of solar radii and solar masses. Saying a star is 2 solar masses instantly places it in context. It tells physicists how it compares to our Sun without needing absolute numbers. In this sense, big becomes shorthand for big relative to something familiar. Alpha Centauri. A being slightly larger than the Sun is meaningful because the Sun is our anchor point. Without that comparison, the number alone would float without intuition. Another way physics interprets bigness is through influence. How far does an object's presence matter? Gravity does not have a cutoff. It weakens with distance following an inverse square law, but it never truly disappears. This means that every object in the universe technically influences every other object, however faintly. In practice, physicists define regions where one object's influence dominates over others. These regions help determine what belongs to a system. In planetary science, this idea appears as a Hill sphere. A planet's Hill sphere defines the region where its gravity dominates over the Sun's gravity for orbiting satellites. For star systems, similar concepts apply. The gravitational reach of Alpha Centauri extends far beyond the stars themselves. The space in which planets could stably orbit, the region where comets might be loosely bound, and the volume of space that responds primarily to the system's combined mass all contribute to how big the system is in a physical sense. This is why size in physics is often inseparable from dynamics. A static picture of an object's dimensions rarely tells the full story. What matters is how things move, how forces act, and how structures remain stable over time. Alpha Centauri stars orbit each other over periods of decades and centuries. Their separation changes, their velocities shift, and their gravitational balance holds steady across timescales far longer than human history. That persistence is a form of size too, not spatial, but temporal. Time itself plays a role in how scale is understood. Large systems often evolve slowly. Small systems tend to change quickly. A molecule vibrates billions of times per second. A planet takes days to rotate and years to orbit. A star system may take centuries for a single orbital cycle. A galaxy can take hundreds of millions of years to complete a rotation. When physicists say something is big, they often mean it operates on long timescales as well as large distances. This connection between size and time becomes especially relevant when we talk about distance measured in light years. A light year bakes time directly into distance. It reminds us that seeing something far away also means seeing it in the past. Alpha Centauri appears to us as it was over 4 years ago. The light reaching our eyes left the stars before recent events on Earth unfolded. This doesn't change the size of the system, but it changes how we interact with it. Big distances separate not just space, but moments. Human intuition struggles here because our brains evolved to navigate meters, not trillions of kilometers. Physics compensates by leaning on mathematics and consistent definitions. Once size, distance, mass, and scale are clearly defined, the equations behave predictably. Orbits can be calculated, energies can be compared, systems can be classified. The universe becomes manageable on paper, even if it remains overwhelming in imagination. It's also worth noting that big is not a value judgment in physics. Bigger does not mean more important. Small particles govern chemistry and biology. Large structures shape cosmic evolution. Alpha Centauri is physically modest compared to giant stars or dense clusters, yet it is profoundly important because of its proximity. Its closeness allows measurements with exceptional precision. It serves as a laboratory for understanding stellar physics, planetary formation, and gravitational dynamics in a system not unlike our own. In physics, size is a collection of relationships. It's how matter fills space, how objects separate, how forces extend, and how systems persist. Alpha Centauri will continue to feel both familiar and immense, because it sits at the intersection of these ideas, close enough to study carefully, large enough to stretch our sense of proportion, and structured in a way that quietly demonstrates how physics handles scale, without ever needing to simplify it away. When Alpha Centauri is mentioned in conversation, it is often spoken about as if it were a single object, a lone star shining quietly in the southern sky. That shorthand is understandable. Our language tends to compress complexity, especially when dealing with astronomical distances. But from a physics perspective, Alpha Centauri is not a single star at all. It is a physical system, a gravitationally bound arrangement of multiple stars, each with its own mass, motion, and role within a shared structure. Understanding how big Alpha Centauri really is requires letting go of the idea of a solitary point of light and replacing it with the idea of an interacting system evolving over time. In physics, a system is defined not just by the objects it contains, but by the interactions between those objects. A single star, isolated in space, would still be governed by internal physics, nuclear fusion, pressure balance, and radiation. But once multiple stars are bound together by gravity, the situation changes. The behavior of each star can no longer be described independently. Their motions, positions, and long-term stability are all connected. Alpha Centauri is one of the closest and most accessible examples of such a system, which makes it especially valuable for understanding how stellar systems behave in general. At the core of Alpha Centauri are two stars commonly referred to as Alpha Centauri A and Alpha Centauri B. These two stars form what is known in physics as a binary system. A binary system is not simply one object orbiting another in a neat circular path. Instead, both objects orbit a shared center of mass. This center of mass, sometimes called the barycenter, is the point around which the system balances. Its location depends on the masses of the two stars. If the stars had equal mass, the barycenter would lie exactly halfway between them. In Alpha Centauri, the stars have similar but not identical masses, so the barycenter lies closer to the more massive of the two, but still outside the physical surface of either star. This detail matters because it immediately expands our notion of size. The system is not defined by the radius of one star or the other. It is defined by the space within which their mutual gravitational influence dominates, and within which their orbital motion unfolds. The distance between Alpha Centauri A and B varies significantly over time. Their orbit is elliptical rather than circular, meaning that sometimes they are relatively close together, and sometimes they are much farther apart. At their closest approach, the stars are separated by a distance comparable to the outer regions of our solar system. At their farthest, the separation becomes several times larger. From a physical standpoint, that changing separation is central to the size of the system. The stars are not fixed points. They move continuously, tracing paths determined by gravity and inertia. Their orbital period is about 80 years, meaning it takes roughly that long for them to complete one full cycle around their shared center of mass. This slow, deliberate motion reflects the scale involved. Large systems move slowly. The greater the distances and masses involved, the longer the timescales over which noticeable changes occur. Beyond this central binary lies Proxima Centauri, a third star that is gravitationally associated with the system. Proxima Centauri is much smaller and less massive than Alpha Centauri A or B. It is a red dwarf, cooler and dimmer than the Sun, and it emits only a tiny fraction of the energy that the larger stars produce. Despite its small physical size, Proxima plays an outsized role in discussions of Alpha Centauri, because it is the closest star to our own Sun. Its proximity has made it a prime target for studies of stellar behavior, planetary systems, and the possibility of habitable worlds. From the perspective of system size, Proxima Centauri dramatically extends the boundaries of Alpha Centauri. Its orbit around the central binary is extremely wide and slow. Estimates suggest that Proxima may take hundreds of thousands of years to complete a single orbit. The distance between Proxima and the central pair is so large that it challenges simple definitions of what it means to be part of the same system. And yet, from a gravitational standpoint, Proxima appears to be weakly bound to Alpha Centauri A and B. Over long timescales, their mutual gravitational attraction is enough to keep them associated. This introduces an important concept in physics. Systems do not always have sharp edges. Unlike solid objects which have clear boundaries, gravitational systems fade gradually into their surroundings. The influence of gravity weakens with distance, but it does not stop abruptly. As a result, defining where a system ends often depends on practical considerations rather than absolute cutoffs. For Alpha Centauri, the inclusion of Proxima means that the system spans a region of space far larger than one might expect, from the brightness or apparent closeness of the stars alone. Another key aspect of viewing Alpha Centauri as a system is recognizing that its components formed together. Stars in binary and multiple systems typically arise from the same collapsing cloud of gas and dust. As that cloud contracts under gravity, it can fragment, forming multiple dense regions that ignite nuclear fusion around the same time. The result is a group of stars born with related compositions and initial conditions, bound together from the start. This shared origin is part of what makes Alpha Centauri a coherent physical system, rather than a chance alignment of unrelated stars. From a physics standpoint, shared origin matters because it influences mass ratios, orbital parameters, and long-term stability. The masses of Alpha Centauri A and B are close enough to produce a stable binary over billions of years. Their orbit has persisted since their formation, resisting disruption from passing stars and the general tidal forces of the galaxy. Proxima's wide orbit makes it more vulnerable to external influences, but its continued association suggests that the system as a whole has remained intact for a very long time. When we think about size in this context, we must also consider energy. The gravitational binding energy of the system is a measure of how tightly its components are held together. A system with high binding energy requires a significant external disturbance to pull it apart. Alpha Centauri's central binary has a relatively high binding energy due to the masses of the stars and their separation. Proxima's binding energy to the system is much lower, reflecting its wide orbit. This difference reinforces the idea that Alpha Centauri is not uniform in structure. It has a dense, tightly bound core and a much looser outer component. This layered structure is common in astrophysics. Many systems have inner regions that are strongly bound and outer regions that are more diffuse. Our own solar system exhibits something similar, with tightly bound inner planets and distant objects in the Kuiper belt and Oort cloud that are only weakly held by the Sun's gravity. In this sense, Alpha Centauri is not exotic. It follows the same physical principles, just applied at a different scale and with stars instead of planets. Another reason it's important to treat Alpha Centauri as a system is that its internal dynamics affect everything that might exist within it. If planets orbit Alpha Centauri A or B, their stability depends on the gravitational influence of the other star. There are regions where planetary orbits can remain stable for billions of years, and regions where they would be disrupted. Physicists model these regions using equations that describe three-body and multi-body interactions, a notoriously complex area of classical mechanics. The presence of multiple stars turns a simple two-body problem into something far richer and more challenging. This complexity again feeds into the idea of size. The system's size is not just the maximum distance between stars, it is also the volume of space within which stable orbits are possible. It is the region where gravity dominates over the background gravitational field of the galaxy. It is the domain in which the motions of objects are primarily shaped by the Alpha Centauri stars, rather than by more distant influences. Considering Alpha Centauri as a system also forces us to think in terms of reference frames. In physics, motion is always measured relative to something else. The stars in Alpha Centauri are not stationary. They move relative to each other, relative to the Sun, and relative to the galaxy as a whole. The entire system is orbiting the center of the Milky Way, carried along by galactic rotation. Within that larger motion, the stars trace their own paths around their shared center of mass. This nested motion adds another layer to the idea of size. Alpha Centauri occupies a certain region of space at any given moment, but that region itself is moving. Over millions of years, the system will drift relative to nearby stars. In the distant past, it was farther away from the Sun. In the distant future, it will be farther again. The size of the system does not change dramatically, but its position within the galaxy does. Physics treats these motions consistently, but our intuition tends to imagine star systems as fixed landmarks. There is also a temporal dimension to size when systems are involved. The stability of Alpha Centauri over billions of years suggests that its physical configuration falls within a stable range. Small systems with unfavorable mass ratios or orbital parameters can become unstable, ejecting members or collapsing into mergers. Alpha Centauri has avoided those outcomes. Its size, mass distribution, and orbital geometry have allowed it to persist. In physics, longevity is often an indicator of a well-balanced system. All of this brings us back to the original question of how big Alpha Centauri really is. When viewed as a single star, the answer would be underwhelming. It would be roughly the size of the Sun. When viewed as a system, the answer expands. It includes the distance between stars, the reach of gravity, the space available for planets, and the timescales over which these relationships endure. The system becomes big not because its components are extreme, but because their interactions unfold across large distances and long periods. When physicists talk about how heavy something is in space, they're almost never talking about weight in the everyday sense. Weight depends on gravity, on where you're standing, and on what is pulling you downward. In space, where objects are in free fall and gravity acts differently depending on distance, weight becomes a confusing and often meaningless concept. Mass, however, is universal. Mass does not change whether an object is on Earth, drifting between stars, or orbiting the center of a galaxy. It is one of the most fundamental quantities in physics, and when it comes to stars, mass is often the single most important number we can know. Mass determines how a star is born, how it lives, and how it eventually dies. It sets the pressure and temperature in the core, which controls the rate of nuclear fusion. It governs how bright the star becomes, how long it shines, and what kind of remnant it leaves behind when its fuel runs out. In systems like Alpha Centauri, mass also dictates how stars move around one another, how tightly they are bound, and how stable the system remains over billions of years. If we want to understand how big Alpha Centauri really is in a physical sense, we need to understand how massive it is, not just as individual stars, but as a combined system. Astronomers measure stellar mass indirectly. Stars cannot be placed on scales, and their interiors are hidden from direct observation. Instead, mass is inferred through motion. Gravity provides the key. When objects orbit each other, their speeds and distances encode information about their masses. This relationship is described by Newton's law of gravitation, and refined through centuries of observation. In binary systems like Alpha Centauri A and B, the orbital motion of the stars around their shared center of mass allows physicists to calculate their masses with remarkable accuracy. Alpha Centauri A is slightly more massive than our Sun. Its mass is about 1.1 times the mass of the Sun. Alpha Centauri B is somewhat smaller, with a mass around 0.9 times that of the Sun. These numbers might not sound dramatic, but in stellar physics, even small differences in mass lead to noticeable differences in behavior. A star with 10% more mass than the Sun will burn its fuel faster, shine more brightly, and evolve more quickly. A star with 10% less mass will burn more slowly and live longer. When combined, Alpha Centauri A and B have a total mass of roughly 2 solar masses. This combined mass is what governs the motion of the central binary system. The barycenter around which they orbit lies in the space between them, closer to Alpha Centauri A because it is slightly heavier. The stars trace elliptical paths around this point, their velocities constantly adjusting as their separation changes. The fact that we can observe this motion over time is what allows astronomers to measure their masses so precisely. Proxima Centauri adds another layer to the picture. Proxima is a red dwarf star with a mass of only about 0.12 times that of the Sun. In absolute terms, it is still enormous by human standards, containing tens of thousands of times the mass of Earth. But compared to Alpha Centauri A and B, it is a lightweight. Its small mass means it contributes relatively little to the total gravitational binding of the system. Nonetheless, it still matters. Its presence increases the total mass of the Alpha Centauri system slightly, and influences how gravity extends outward from the central pair. Taken together, the Alpha Centauri system has a total mass a little over 2 solar masses. From one perspective, that makes it modest. There are stars in our galaxy with tens or even hundreds of times the mass of the Sun. There are dense clusters containing thousands of stars bound together. Compared to those, Alpha Centauri is not especially heavy. But mass in physics is always relative. Compared to our solar system, which is dominated by a single star, Alpha Centauri is heavier, more complex, and capable of shaping a larger region of space through its combined gravitational influence. Mass also determines how far a system's gravity can meaningfully dominate its surroundings. While gravity technically extends infinitely, its practical influence diminishes with distance. The combined mass of Alpha Centauri means that within a certain region of space, the motion of smaller objects would be governed primarily by its stars, rather than by the gravity of the Milky Way or other nearby stars. This region is part of what defines the system's physical size. A more massive system commands a larger gravitational domain. Another way mass expresses itself is through energy output. There is a strong relationship between a star's mass and its luminosity. More massive stars have hotter cores, which increases the rate of nuclear fusion. That leads to much higher energy output. Alpha Centauri A, being slightly more massive than the Sun, is also more luminous. It emits more energy per second and appears brighter when viewed from a fixed distance. Alpha Centauri B, with its lower mass, emits less energy and shines more softly. Proxima Centauri, despite being the closest star to the Sun, is intrinsically faint because of its low mass. Its core temperature is lower, fusion proceeds more slowly, and its luminosity is only a tiny fraction of the Sun's. This contrast highlights why mass is more important than distance when it comes to intrinsic brightness. Proxima appears dim not because it is far away, but because it simply does not produce much energy. Mass also controls a star's lifespan. More massive stars live fast and die young. They burn through their nuclear fuel quickly and often end their lives in dramatic events like supernovae. Less massive stars burn slowly and steadily, lasting for billions or even trillions of years. Alpha Centauri A, with its slightly higher mass, will exhaust its hydrogen fuel sooner than the Sun. Alpha Centauri B will last longer. Proxima Centauri, with its very low mass, is expected to shine for far longer than the current age of the universe. This difference in lifespans has implications for the system as a whole. Over immense timescales, the stars will evolve at different rates. Their sizes, luminosities, and internal structures will change. These changes will alter the gravitational and radiative environment within the system. In physics, systems are rarely static. Mass determines not just the present state, but the entire evolutionary path. Comparing Alpha Centauri to the Sun in terms of mass also helps ground our understanding. The Sun contains about 99.8% of the mass of the entire solar system. The planets, asteroids, comets, and dust make up the remaining fraction. This concentration of mass creates a simple gravitational hierarchy. Planets orbit the Sun. Moons orbit planets. Everything falls neatly into place. Alpha Centauri, by contrast, spreads its mass across multiple stars. There is no single dominant center in the same way. Gravity is shared, balanced, and negotiated through motion. This shared mass distribution is what makes binary systems dynamically rich. It also complicates the formation and stability of planets. In a single star system, planets can orbit relatively undisturbed. In a multi-star system, the gravitational pull of companion stars can perturb orbits, leading to complex trajectories. Whether stable planetary orbits exist around Alpha Centauri A or B depends on mass ratios, distances, and orbital geometry. Physics provides tools to model these situations, but the outcomes are not always intuitive. Mass also connects directly to how systems respond to external influences. Passing stars, galactic tides, and molecular clouds can perturb stellar systems. A more massive system resists disruption more effectively. Alpha Centauri's central binary is tightly bound and relatively resistant to being pulled apart. Proxima's wide orbit makes it more vulnerable, but the combined mass of the system has so far kept it attached. Over billions of years, this balance has held. From another angle, mass influences how we detect and study systems. The gravitational pull of Alpha Centauri A and B on each other produces observable effects that allow mass measurement. The gravitational pull of Proxima on nearby objects can reveal the presence of planets through subtle stellar motions. In modern astrophysics, mass often reveals itself through its effects rather than its presence. We see how stars wobble, how light shifts, and how orbits behave, and from those clues we infer how heavy the system must be. As we think about bigness in physics, mass provides a different sense of scale than size or distance. Alpha Centauri is not enormous because its stars are exceptionally heavy. It is significant because it combines familiar stellar masses into a system whose total gravitational influence extends across a large region of space. It is heavy enough to bind multiple stars together, shape potential planetary systems, and persist as a stable structure within the galaxy. Instead of asking how heavy a star is, imagine approaching the question from a different angle, one that feels more geometric than gravitational. Imagine asking how much space a star actually takes up. how wide it is, how far its surface extends from its center, how much volume is enclosed inside that glowing sphere of plasma. This shift in perspective moves us from mass to radius, from how strongly a star pulls on its surroundings to how large it physically is. And while these ideas are related, they are not the same. In physics, mass and size can diverge in ways that feel counterintuitive, especially once stars enter the picture. Stellar radius is a deceptively simple term. It refers to the distance from the center of a star to its surface. For solid objects, a surface is easy to define. For stars, which are made of hot, ionized gas with no sharp boundary, the idea of a surface becomes more subtle. Physicists usually define a star's radius as the point where the gas becomes transparent enough for light to escape freely. Below that point, photons are constantly scattered and absorbed. Above it, light can travel outward into space. This boundary is not rigid, but it is consistent enough to serve as a useful definition. Using this definition, Alpha Centauri A has a radius about 1.2 times that of the Sun. Alpha Centauri B is smaller, with a radius around 0.86 times the Sun's. These differences might seem modest, but even small changes in radius translate into large changes in volume. Volume scales with the cube of the radius. If one star has a radius that is 20% larger than another, its volume is not 20% larger. It is closer to 73% larger. This cubic relationship is one of the reasons stellar size quickly becomes unintuitive. To ground this, consider the Sun. Its radius is about 696,000 kilometers. That means you could line up more than 100 Earths across its diameter. Alpha Centauri A, being about 20% larger in radius, encloses significantly more space. Its volume is roughly 1.7 times the Sun's volume. That extra space is not empty. It is filled with plasma at varying densities and temperatures, all held together by gravity and balanced against the outward pressure generated by nuclear fusion in the core. Alpha Centauri B, by contrast, is smaller than the Sun. Its radius is reduced, and its volume is only about 0.64 times the Sun's volume. Despite having nearly the same mass as the Sun, Alpha Centauri B packs that mass into a smaller volume. This means it has a higher average density. Density is mass divided by volume, and this difference highlights an important point in stellar physics. Bigger does not always mean heavier, and smaller does not always mean less massive. Stars can be compact or bloated depending on their internal structure, composition, and stage of evolution. Proxima Centauri pushes this contrast even further. Its radius is only about 14% that of the Sun. In terms of volume, that makes it incredibly small compared to Alpha Centauri A and B. Its volume is less than 1% of the Sun's volume, and yet it is still a star, sustained by nuclear fusion in its core. This illustrates how wide the range of stellar sizes can be, even within a single system. From a physics perspective, stellar radius is determined by a balance of forces. Gravity pulls matter inward, trying to compress the star. Pressure generated by nuclear fusion pushes outward, trying to make the star expand. The equilibrium between these two forces sets the star's size. For more massive stars, gravity is stronger, which tends to compress the star. At the same time, higher mass leads to higher core temperatures and faster fusion, increasing outward pressure. The resulting radius depends on which effect dominates. This is why the relationship between mass and radius is not linear. Doubling a star's mass does not double its radius. In some mass ranges, stars get larger as mass increases. In others, they get smaller. Red dwarfs, like Proxima Centauri, are relatively compact despite being fully fledged stars. Massive stars can be much larger than the Sun, but once stars exhaust their fuel and become white dwarfs, neutron stars, or black holes, their radii can shrink dramatically while retaining substantial mass. In the case of Alpha Centauri A and B, both stars are still in a stable phase of their lives known as the main sequence. They are fusing hydrogen into helium in their cores, much like the Sun. Their sizes reflect this shared evolutionary stage. Alpha Centauri A is slightly more massive, which leads to a hotter core and a slightly expanded outer envelope. Alpha Centauri B, with its lower mass, maintains a tighter structure. Volume becomes especially interesting when we consider how matter is distributed inside these stars. A star is not uniformly dense. The core is much denser than the outer layers. In the Sun, the core contains about half the Sun's mass within just a quarter of its radius. The outer layers are comparatively diffuse. This means that most of the star's volume contains relatively little mass. The same is true for Alpha Centauri A and B. Their impressive volumes do not imply solid fullness. They imply extended regions of hot, low-density plasma. This is one of the reasons stars can appear paradoxical. They are enormous, yet if you could somehow scoop up a cupful of stellar material from the outer layers, it would weigh very little. At the same time, the core is so dense and energetic that conditions there cannot be replicated on Earth. Size, volume, and density intertwine in ways that resist simple analogy. Thinking in terms of volume also helps clarify what stars are not. They are not hollow shells. They are not burning like flames. They are massive, self-gravitating spheres of plasma where energy is generated at the center and transported outward through radiation and convection. The radius marks the point where this energy finally escapes. Everything inside contributes to the star's structure, even if the outer regions dominate its visible size. When we compare the sizes of the Alpha Centauri stars to the solar system, the contrast becomes striking. The Sun's radius, enormous as it is still tiny compared to the distances between planets. Earth orbits at about 215 solar radii from the Sun's center. Neptune orbits at roughly 4,500 solar radii. If you placed Alpha Centauri A at the center of such a system, its larger radius would barely change the scale of planetary orbits. This reinforces the idea that stars, though huge by human standards, are still small compared to the spaces they inhabit. This observation becomes even more relevant when we think about the Alpha Centauri system as a whole. The distance between Alpha Centauri A and B ranges from about 11 astronomical units at closest approach to about 35 astronomical units at their farthest separation. These distances dwarf the sizes of the stars themselves. Even at their closest, the stars are separated by tens of millions of kilometers of empty space. Their physical radii barely register on that scale. From a system's perspective, the stars are compact nodes connected by gravity across vast distances. Their volumes matter for internal physics, but the structure of the system is dominated by separation, not size. This is a recurring theme in astrophysics. Objects are dense islands in a sea of emptiness. Their sizes are impressive, but the voids between them are larger still. Another important aspect of stellar radius is how it changes over time. Stars do not maintain a fixed size throughout their lives. As they exhaust hydrogen in their cores, they begin to change. The core contracts, heating up further, while the outer layers expand. Eventually, stars like Alpha Centauri A and B will become red giants, swelling to many times their current radii. During that phase, their volumes will increase dramatically, even as their masses remain nearly the same. This future evolution matters because it shows that stellar size is temporary. What we measure today is a snapshot. The current radii of the Alpha Centauri stars reflect their present balance of forces, not a permanent condition. Over billions of years, those radii will change, altering the environment within the system. Planets that might be stable today could be engulfed or destabilize in the distant future. Proxima Centauri, on the other hand, will change very little over comparable timescales. Its low mass means it burns fuel extremely slowly. Its radius will remain relatively constant for trillions of years. In this sense, Proxima's small size is linked to longevity. Smaller stars live longer lives. Larger stars live faster, more dramatic ones. Volume also plays a role in how stars interact with radiation and surrounding space. A larger surface area means more opportunity to emit energy. Alpha Centauri A's larger radius contributes to its higher luminosity alongside its higher core temperature. Alpha Centauri B's smaller radius limits its surface area and energy output. Proxima's tiny radius results in a very small emitting surface, contributing to its faintness. Yet surface area alone does not determine habitability or influence. Proxima Centauri's small size does not prevent it from hosting planets, including at least one that orbits relatively close due to the star's low luminosity. In fact, the small radius allows planets to orbit close enough to receive warmth while remaining gravitationally bound. Here again, size interacts with other properties in non-obvious ways. Returning to the idea of bigness, stellar radius answers a very specific question. It tells us how large the stars themselves are as physical objects. It does not tell us how far their influence extends. It does not tell us how massive they are. It does not tell us how far apart they are. But it provides a crucial piece of the puzzle. Without knowing the size of the stars, we cannot fully understand their density, luminosity, or evolutionary paths. Alpha Centauri, when viewed through the lens of stellar radius and volume, becomes a study in restrained variation. None of its stars are extreme outliers. None push the boundaries of known physics. Instead, they occupy familiar positions along the spectrum of stellar properties. This familiarity is precisely what makes the system valuable. It allows physicists to test theories under conditions that are close to home, both literally and conceptually. Distance inside a star system is not about empty space alone. It is about motion, balance, and the quiet negotiation between gravity and inertia that plays out over years, decades, and sometimes millennia. When we turn our attention to the separations inside the Alpha Centauri system, we are no longer asking how large the stars are as objects, but how far apart they remain while still belonging to one coherent physical structure. This shift is important, because in astrophysics, systems are defined far more by distances and motion than by the sizes of the objects themselves. Within Alpha Centauri, the most important distances are orbital distances. These are not fixed lengths like the diameter of a table or the height of a building. Orbital distances change continuously as objects move along their paths, responding to gravity while conserving energy and angular momentum. Every orbit is a compromise between falling inward and moving sideways. The result is not collapse, but repetition, motion that returns again and again to familiar configurations without ever being exactly the same. At the heart of the system, Alpha Centauri A and Alpha Centauri B orbit one another in a long, slow gravitational dance. Neither star is stationary, both move. The phrase, "one star orbiting another," is convenient but incomplete. In reality, both stars orbit a shared center of mass. This point, invisible and empty, lies somewhere between them, closer to the more massive star but not located inside either stellar body. The distance from each star to this center of mass depends on its mass, and the total separation between the stars depends on where they are in their orbit. The orbit of Alpha Centauri A and B is elliptical, not circular. This means the distance between them varies over time. At their closest approach, known as periastron, the stars are separated by roughly 11 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. To put that in perspective, Saturn orbits the Sun at about 9.5 astronomical units. So at their closest, Alpha Centauri A and B are separated by a distance comparable to the Sun-Saturn separation. Even then, they are extraordinarily far apart compared to their own sizes. Their stellar radii, measured in fractions of an astronomical unit, are tiny against this backdrop. At their farthest separation, called a pastron, the distance between Alpha Centauri A and B grows to about 35 astronomical units. This is farther than Neptune's average distance from the Sun. Over the course of their orbit, the stars swing between these extremes, speeding up as they approach each other and slowing down as they move apart. This behavior follows directly from the conservation of angular momentum and the laws of gravitation described by Kepler and Newton. The orbital period of this central binary is about 80 years. That number is itself a reflection of distance. Wider orbits take longer to complete. The fact that the stars take decades to complete a single revolution tells us that the scale of their separation is large. No human lifetime can casually observe a full orbit without careful record-keeping and patience. Astronomers have been tracking the relative motion of these stars for centuries, slowly building a precise picture of their orbital parameters. From a physics perspective, these distances determine more than just motion. They define regions of stability. Around each star there exists a zone where planets could orbit stably without being torn away or destabilized by the gravitational pull of the companion star. These regions depend sensitively on the separation between the stars and the shape of their orbit. When Alpha Centauri A and B are close together, their gravitational influence overlaps more strongly, shrinking the regions where planets could maintain stable paths. When they are farther apart, those regions expand. This introduces an important idea. Orbital distance is not just a number, it is a constraint. It sets limits on what structures can exist within a system. In the Alpha Centauri system, the varying distance between the stars means that stability is dynamic. Any planet orbiting one star must remain stable across the entire binary orbit, not just at one moment. Physics demands long-term consistency, not temporary alignment. Beyond the central binary lies Proxima Centauri, whose distance from Alpha Centauri A and B is far greater. Proxima's separation is measured not in tens of astronomical units, but in thousands. Estimates place Proxima's average distance at roughly 13,000 astronomical units from the central pair, though this value is uncertain due to the immense orbital period involved. At that distance, Proxima is more than 400 times farther from Alpha Centauri A and B than Neptune is from the Sun. This immense separation changes the character of Proxima's orbit entirely. While Alpha Centauri A and B form a tightly bound binary, Proxima is only loosely attached to the system. Its gravitational bond is weak, but still sufficient to keep it associated over long timescales. Proxima's orbital period is estimated to be on the order of hundreds of thousands of years. This means that from a human perspective, Proxima appears almost stationary relative to the central pair. Here, the meaning of orbital distance stretches again. Proxima's separation is so large that external influences become significant. Passing stars, galactic tides, and the gravitational field of the Milky Way itself all exert forces comparable to the pull of the central binary at that distance. This places Proxima in a delicate balance. It remains part of the Alpha Centauri system, but just barely. Small perturbations over millions of years could alter its orbit significantly. In physics, this kind of structure is common. Systems often have dense cores and diffuse outskirts. The Alpha Centauri system exhibits this pattern clearly. The inner region, dominated by the binary, is compact and strongly bound. The outer region, where Proxima resides, is expansive and fragile. Together, they define the system's full spatial extent. Understanding these distances also helps clarify what close means in astronomy. Alpha Centauri is the closest stellar system to our own, yet its internal distances dwarf anything we experience in daily life. Even the smallest separation between Alpha Centauri A and B represents billions of kilometers of space. And yet, in galactic terms, these distances are modest. Stars in dense clusters can orbit each other at comparable or even smaller separations. On the other hand, many stars in the galaxy are separated by distances far greater than those within Alpha Centauri. Orbital distances also determine how energy flows through the system. The stars exchange gravitational energy as they move along their elliptical paths. This exchange keeps the system stable without requiring any external input. Over time, tiny amounts of energy can be transferred to passing objects or radiated away through gravitational interactions, but the overall structure remains intact. Physics treats this as a bound system with negative total energy, meaning it would take energy input to pull it apart. There is also an important geometric aspect to these distances. Orbits are not confined to flat planes in a simple way. The orbital plane of Alpha Centauri A and B is tilted relative to our line of sight from Earth. This tilt affects how we observe their separation over time. Sometimes the stars appear closer together in the sky. Sometimes they appear farther apart. These apparent changes are projections of their true three-dimensional motion. By carefully modelling this geometry, astronomers can reconstruct the real orbital distances. This process highlights another subtle point. Distances inside star systems are not always measured directly. They are inferred through motion, angles, and time. Physics relies on consistency across observations. If the same orbital parameters explain centuries of data, the distances involved must be correct. Alpha Centauri's binary orbit is one of the best-studied stellar orbits precisely because it is nearby and slow enough to track accurately. The scale of orbital distances also affects how we think about travel, even hypothetically. When people imagine journeys to Alpha Centauri, they often focus on the distance from Earth to the system, measured in light years. But once there, navigating within the system would still involve immense distances. Travelling from one star to another would take years, even at speeds far beyond current technology. The system may be close by cosmic standards, but internally it remains vast. These distances also shape the potential for interaction between stars and any surrounding material. Stellar winds, radiation, and magnetic fields weaken with distance. At the separation between Alpha Centauri A and B, these effects are minimal. The stars do not significantly influence each other's atmospheres or fusion processes. Their interaction is almost entirely gravitational. This separation ensures that each star evolves largely independently, despite being part of the same system. Comparing this to tighter binary systems reveals how distance changes behavior. In very close binaries, stars can exchange mass, distort each other's shapes, and dramatically alter their evolution. Alpha Centauri's relatively wide separation prevents these effects. The system is calm, orderly, and long-lived. Distance here acts as a stabilizing factor. As attention shifts outward again, the role of orbital distance becomes even more pronounced. Proxima's planets, for example, orbit extremely close to their star because Proxima is dim and small. Their distances are measured in fractions of an astronomical unit. This is the opposite end of the scale from Proxima's orbit around the central binary. The same system contains orbital distances ranging from millions of kilometers to trillions. Physics accommodates this range without contradiction, but intuition struggles to hold it all at once. The Alpha Centauri system, viewed through the lens of orbital distances, becomes a study in layered scale. Close distances define stellar structure. Intermediate distances define binary motion. Vast distances define loose association. Each layer obeys the same physical laws, but the outcomes differ because distance sets the context in which those laws operate. As this picture settles, it becomes clear that understanding Alpha Centauri requires thinking less about objects and more about relationships. The stars are not important only because of what they are, but because of how far apart they are and how they move together through space. These distances are what give the system its shape, its stability, and its quiet complexity. Gravity does not announce itself with sound or light. It does not have edges, surfaces, or visible structures, and yet without it, Alpha Centauri would not exist as a system at all. The stars would simply drift through the galaxy as unrelated travelers, passing near one another once and never meeting again. What makes Alpha Centauri more than a coincidence of nearby stars is gravitational binding, the condition that turns proximity into permanence and motion into structure. In physics, gravitational binding is not a vague idea. It has a precise meaning. A system is gravitationally bound when the total energy of its components is negative. That statement may sound abstract, but it captures something very concrete. Negative total energy means that the objects involved do not have enough kinetic energy to escape one another's gravitational pull. They can move, orbit, and shift positions, but they remain confined. To separate them completely, energy would have to be added from the outside. This definition is what allows physicists to decide whether something is truly a system or just a temporary arrangement. Two stars passing near each other are not a system if their trajectories carry them apart forever. Two stars orbiting a shared center of mass are a system because gravity has locked them into a long-term relationship. Alpha Centauri qualifies as a system because its stars are gravitationally bound, not just momentarily close. At the center of Alpha Centauri, the binding between Alpha Centauri A and Alpha Centauri B is strong and unambiguous. Their masses are comparable to the Sun's, and their separation, while large, is well within the range where gravity dominates their motion. Each star continually accelerates toward the other, but their sideways motion prevents collapse. The result is a stable orbit that has persisted for billions of years. This stability can be quantified. Using Newtonian gravity, physicists calculate the gravitational potential energy of the system and compare it to the kinetic energy of the star's motion. The numbers show that the stars are deeply bound. Their relative velocities are far below what would be required for escape. Even if a passing star nudged the system slightly, it would not be enough to break the bond between Alpha Centauri A and B. The system has a gravitational depth, a kind of energy well that the stars sit inside. This idea of a gravitational well is useful for intuition. Imagine a smooth, shallow bowl. A marble placed inside will roll around but remain trapped unless you give it a strong push. The deeper the bowl, the harder it is to remove the marble. Alpha Centauri A and B sit in a gravitational bowl shaped by their combined mass. That bowl is deep enough to keep them together across cosmic time. The situation becomes more subtle when Proxima Centauri enters the picture. Proxima is much less massive and much farther away. Its gravitational bond to the central binary is weak. In energy terms, Proxima sits near the edge of the system's gravitational well. Its orbital speed is low, and its separation is large. This places it in a marginally bound state. It is held but not tightly. Physicists care about this distinction because weakly bound objects are vulnerable. A close encounter with another star, or the cumulative effect of the Milky Way's tidal field, could alter Proxima's orbit significantly. Over millions or billions of years, such influences can add or remove energy from Proxima's motion. If enough energy is added, Proxima could escape entirely, becoming an independent star drifting through the galaxy. That possibility does not mean the system is unstable in the short term. It means that gravitational binding is not binary, it is a spectrum. Alpha Centauri A and B are strongly bound. Proxima is weakly bound. Both conditions still qualify as binding, but they behave differently over long timescales. Physics allows for this nuance, and Alpha Centauri provides a nearby example of how binding strength varies within a single system. Another important aspect of gravitational binding is that it depends on relative motion, not absolute motion. Alpha Centauri as a whole is moving rapidly through the galaxy. It orbits the center of the Milky Way at hundreds of kilometers per second. This motion does not weaken the system's internal binding. What matters is how fast the stars move relative to one another. As long as their internal motions remain below escape velocity, the system stays intact. Escape velocity is a key concept here. It is the minimum speed an object must reach to break free from a gravitational field without further propulsion. For Earth, escape velocity is about 11.2 kilometers per second. For the Alpha Centauri binary, escape velocities depend on distance. Close to one of the stars, escape velocity is high. Farther away, it drops. Proxima's orbit exists in a region where escape velocity is low, which is why its binding is fragile. Gravitational binding also explains why the Alpha Centauri system has a defined size, even though gravity technically extends forever. In practice, physicists define the system's boundary as the region within which objects remain bound over long timescales. Beyond that region, external gravitational influences dominate. For Alpha Centauri, this boundary is set not by the star's physical sizes, but by the balance between their gravity and the background gravitational field of the galaxy. This balance introduces the idea of tidal forces. The Milky Way's gravitational field is not uniform. It changes slightly across space. These differences exert tidal forces that can stretch and distort stellar systems. In dense environments, tidal forces can tear systems apart. Alpha Centauri resides in a relatively calm region of the galaxy, where tidal forces are weak. This allows even a loosely bound component like Proxima to remain attached for long periods. Binding energy also connects directly to formation. Alpha Centauri's stars likely formed from the same collapsing cloud of gas. During formation, gravitational potential energy was converted into heat and radiation, allowing the cloud to fragment and condense into multiple stars. The energy lost during this process helped to lock the system together. Without sufficient energy loss, the stars would not have become bound. Formation and binding are inseparable. Once a system is bound, gravity continues to shape its internal evolution. Orbits can change slowly through processes like angular momentum exchange, stellar winds, and interactions with surrounding matter. In Alpha Centauri, these processes are subtle. The stars are widely separated, and their winds do not interact strongly. As a result, the system evolves quietly, with little internal disruption. Gravitational binding also determines how the system responds to intruders. When another star passes nearby, its gravity can perturb the Alpha Centauri system. The effect depends on the mass of the intruder, its speed, and its distance of closest approach. For the central binary, only a very close and massive encounter would matter. For Proxima, even a more distant pass could have noticeable effects. This difference again reflects binding strength. From a physics standpoint, binding is what allows long-term prediction. If Alpha Centauri were not bound, its future configuration would be trivial. The stars would separate and the system would dissolve. Because it is bound, its future can be modeled, orbits can be projected, stability can be assessed. This predictability is one of the reasons bound systems are central to astrophysics. Binding also sets the stage for everything else we care about. Planets, if they exist, are bound to their host stars. Moons are bound to planets. Galaxies are bound collections of stars. Clusters are bound collections of galaxies. At every scale, gravity creates structure by binding matter together. Alpha Centauri is one link in this hierarchy, neither tiny nor immense, but governed by the same principles as everything else. It is worth emphasizing that gravitational binding does not imply rigidity. Bound systems are dynamic. The stars of Alpha Centauri are constantly moving. Distances change. Velocities shift. What binding guarantees is not stillness, but confinement. The motion remains organized rather than dispersive. Energy circulates rather than escapes. This idea helps reconcile two seemingly opposite facts. Alpha Centauri is vast internally, with enormous distances between its stars. At the same time, it is cohesive. Gravity bridges those distances effortlessly. In physics, distance alone does not weaken gravity beyond recognition. What matters is mass and relative motion. Given enough mass and slow enough speeds, gravity can hold together structures that span trillions of kilometers. As this understanding settles, the role of gravitational binding becomes clearer. It is the reason Alpha Centauri persists as a recognizable system. It is the reason its stars remain neighbors rather than strangers. It's the quiet condition that allows all other questions about size, distance, energy, and evolution to be meaningful. Long before numbers appear on a page, distance in astronomy begins as a problem of geometry and patience. Nothing about measuring how far away a star is can be done directly. There are no rulers long enough, no markers placed along the way, no straightforward sense of scale to rely on. Instead, physicists and astronomers are forced to work indirectly, using motion, angles, and the finite speed of light as their tools. When it comes to Alpha Centauri, our nearest stellar neighbor, this indirect approach is not just useful, it is unavoidable. The most fundamental method used to measure the distance to nearby stars is parallax. Parallax is not a complex idea, but its implications are profound. It relies on a simple geometric effect that most people have experienced without thinking about it. If you hold a finger out in front of your face and alternately close one eye and then the other, your finger appears to shift position against the background. The finger has not moved. Your point of view has. The closer the finger is to your face, the larger that apparent shift appears. The farther away it is, the smaller the shift becomes.